When we talked about random variables, we said that one of the reasons that we like random variables is because it lets us average results. So, for example, I can't average a head and a tail. I don't know what that is, right? You know, edge. I don't know. You know, that's just not a good concept. But if I say that heads are 0 and tails are 1, then I can actually average a head and a tail and say that the average is a half, right? Because that's just averaging numbers, 0 and 1. Okay, so that's kind of what we want to do with random variables, and we usually use the word expected value to mean that. Okay, so let's take a look. Let's average the random variable x, which is related to rolling a die, and it just simply counts the number of dots on the face of the top of the die when it finishes rolling. So what I have is 1 through 6, right? And the probabilities of each outcome are the same. It's equally likely. So there's a 1/6 probability that I get a 1. There's a 1/6 probability I get a 2, or a 3, or a 4, or a 5, or a 6. Okay, so I simply have to add those, and what we'll do is we'll factor out the 1/6, and what I have here is 1 plus 2 plus ... up to plus 6. But that's actually an arithmetic series, so it's n times the first element, 1 plus the last element, and then divided by 2. It's just Gauss's trick, right? And that ends up being 21 over 6, which is 3.5. Okay. Now I want to pause for a second here, because you know, like I said, we're gonna call this the expected value. Okay, and that is such a misleading term. Okay, and here's why it's misleading. Let's say that I'm actually going to roll a die right now. Do I expect to get 3.5? No, right? That's an absurd solution. If I flip a coin, I don't expect to get a half, right? I expect to get heads or tails, 0 or 1, not a half. I expect to get a 1, a 2, a 3, a 4, a 5, or a 6 when I roll a die, not 3.5. Okay, so what's really happening is this. Let's take our roll and let's roll 600 dice, okay? Or one die 600 times. All right, so because the probabilities are the same, I might expect, okay, 100 ones, 100 twos, 100 threes, 100 fours, 100 fives, and 100 sixes. Okay. Now, between you and me, if you actually do this experiment, you're probably not going to get exactly 100 ones. You might get 98. You might get 105, and so on. But the probabilities are such that this is a reasonable expectation. Okay. Now, if I average this, I'm actually going to get, well, let's see. I'm going to get 3.5 times 100. Okay. So if I average them, I'm actually going to get like 350. Okay. That is reasonable. Okay. Oh, wait a minute. I've rolled 600 die. So no, not 350. It's actually 3.5 times 600. Okay. And that's what? 2100. Okay. So yeah. I was looking at the hundreds. Okay. So that is a reasonable sum, I should say, right? Which averages to 3.5 per roll of the die. Okay, so it's in that sense that that this is an expected value, right? It is simply the average after a large number, okay, a large number of repeated experiments. Okay, the larger, the closer we're going to come to actually getting that expected value in the average. Okay, so let's go ahead and continue here, and our next question is going to be this. Suppose that we roll 2 dice, right? And our expected, a random variable is simply the sum of those outcomes, okay? So now, what am I going to get? Well, let's see. I could have gotten a 2, right? And I got a 2 if I rolled a 1 and then a 1. And that's actually the only way to get 2. So the probability of that happening is 1 out of 36. Now, where's the 36 coming from? Just from the counting argument, right? I have 2 dice. There's 6 ways to do that, 6 ways to do that, 36 total, okay? Okay, and now what about getting a 3? Well, I can get a 1 and a 2, or I can get a 2 and a 1, right? Both of those have the same random variable 3, and so there's 2 out of 36 ways, right? That's the probability. Okay. Now what about 4? Well, I can get a 1 and a 3, a 2 and a 2, a 3 and a 1, and that's kind of the only way for that to happen. So there's 3 out of 36 ways, right? And so on. When we get to 7, that's actually the most likely scenario because you can get a 1 and a 6, a 2 and a 5, a 3 and a 4, 4 and a 3, 5 and 2, 6 and 1, right? You know, so there's all those ways. There's 6 different ways of doing that. 12, there's only one way, a 6 and a 6, right? So these are the probabilities of each of the individual outcomes. So how do I get the expected value or the average of x? The same way. We take the probability, right? And then the value of x. The probability and then the value of x and so on, right? We add all those. This is just a weighted average of the possible values of x weighted by the probability that that value actually comes up. And like I said, that has to do with the, if I were to repeat this experiment many times, let's say 12 million times, then that's the average that would result. Okay. All right. So in this case, the answer turns out to be 7. And by the way, that's suspicious, right? Because if I roll one die, the expected value was 3.5. 2, I get 7. Do we see a pattern, right? Okay, let's make that formal, okay? We're calling it expected value, and I'm not actually going to define it, okay? So the expected value, and is written as E of x, right, is actually the sum over all possible values, right, of the, which are of the random variable. So if the random variable goes from 2 to 12 is the sum over 2, 3, 4, 5, up to 12, of the actual random variable, right? So k, which is the outcome, times the probability, right? Weighted by the probability that the result is actually equal to k. And remember, that is the probability of a set. Okay, so that's how we compute it, right? And that's just the formal definition. And now here's an interesting theorem, okay? Because the way that we did the summation was we summed over the output of the random variable, right? The random variable gave me a 2 up to a 10, right? Here's the different way of doing it. We're going to sum, instead of summing over the random variable, right? Right here, I'm summing over the states, right? And what I say is, oh, add up all the states, right? So each card in a deck of cards, there's 52 states. And what we'll do is we'll do the random variable that, or rather the value that the random variable assigns to that state times the probability of that one little state, okay? And these two are actually the same, okay? You should be able to prove this. You know, the key to this proof is that when I look at the events, such as the probability that x is equal to 3, which is an event, that is adding up the probabilities of the states in that set, x equal to 3. And since the states are disjoint, adding them up is just as simple as adding them up. And here I have an addition that essentially goes across rows, if you will, versus a different addition or sum that goes across columns, right? So it ends up being the same. But anyway, like I said, that's something that you should be able to do. It's not a particularly hard proof, but do convince yourself that it's true. Okay. Here are some other things that you should be able to prove. And by the way, the proofs are straightforward simply because what we're doing is we're adding numbers, okay? So here's one proof. If x is a random variable, let's define a new random variable by y of s is equal to x times x of s, right? So for example, let's say that x of s is the number in a card from a deck of cards, right? So k, let's say, is 2, right? So y of s would do something like this. Y of the 5 of hearts, right, is equal to 10 because it's 2 times x of the 5 of hearts, and the 5 of hearts would just be 5, right? So that's how we're defining these random variables, just as some arithmetic operation on an old random variable. Okay, so now if I ask what is the expected value of y, it ends up being simply k times the expected value of x. Why? Because I take the sum, which would have k times the expected value of x times the probability, right, of the event, and we'll just take the k out of the sum, and we end up with k times the expected value of x. Okay. Likewise, if I have two random variables, I define a new one as the sum of those two random variables. Okay. Then the expected value of the sum is in fact the sum of the expected values. again, I have a sum, right, of basically a sub I plus b sub I, right? And I'm just factoring that as the sum of the a sub I plus sum of the b sub I, okay? That's the basic reason why that theorem holds. And what's nice about this is that now if I talk about linear combinations of random variables, and that just means I'm adding up some multiples of random variables, then the expected value is the exact same combination, but of the expected values. So that's great, okay? And that does justify now why the expected value of adding up rolling 2 dice is in fact the same thing as rolling 1 die plus the expected value of rolling another die, right? And that's comforting.